Hello, my name is Alexandre Gomes de Siqueira. In this work, we investigate how calibration affects the perception of tangible object size in near-field virtual reality. Specifically, we study how mismatches between visual and haptic information influence how users perceive the size of graspable objects in immersive environments. Virtual reality systems increasingly incorporate tangible physical objects to support realistic interaction. Examples include medical training simulations, industrial control interfaces, and immersive training systems. However, the effectiveness of these systems depends on how accurately users perceive object properties such as size. Prior research has shown that users often misperceive object sizes in VR environments. Our focus is on studying graspable tangibles. They are physical objects that users manipulate while interacting with their virtual representations. They provide passive haptic feedback and allow natural manipulation through grasping or rotation. These interactions can improve presence and realism in immersive environments. However, integrating visual and haptic cues can also create perceptual conflicts. Previous research has shown that perception in virtual environments differs from real world perception. Several studies report distortions in spatial and size judgments. In particular, haptic perception alone often produces larger size overestimations than visual perception. These findings motivated our investigation of calibration effects on size perception. In this context, our research question is: does visual haptic fine motor interaction calibrate users' near field size perception of tangibles in virtual reality? We hypothesize that near field visual haptic fine motor interaction does calibrate the perception of the size of tangibles in VR. We investigate whether exposure to mismatches between physical and virtual objects during calibration affects later size judgments. In our study, participants sat between a tracking table and a reporting screen while wearing a head-mounted display. They interacted with 3D printed physical dials that were also rendered in the virtual environment. The virtual scene replicated the physical setup to ensure accurate spatial alignment between real and virtual objects. Participants used an HTC Vive headset to view the virtual environment, which was implemented using the Unity game engine. The study consisted of three phases. First, participants completed a pretest in which they perceived and reported dial sizes following one of two conditions: vision only or haptics only. Next, they went through a calibration phase where they both saw and touched the dials but did not report sizes. During the post-test phase, they performed the same estimation and reporting tasks as in the pretest. In the vision-only condition, participants could only see but not touch and report dial sizes during pre- and post-test phases. In the haptics-only condition, participants could only touch and report the dial sizes without visual input of the dial in VR. This allowed us to isolate the effects of each perceptual modality. During calibration, participants could see and touch dials, and we introduced three types of perturbations. In the divergent plus condition, the physical dial was 10% larger. In the convergent condition, physical and virtual dials were the same size. In the divergent minus condition, the physical dial was 10% smaller. These perturbations allowed us to study calibration effects. In total, this between-subject study had 6 conditions: vision or haptic only times 3 calibration conditions. This video shows calibration. We opted not to render end effectors' arms and hands to avoid body scaling effects. This slide describes the experimental procedure. After having signed an informed consent form, participants answered a quick demographic survey, after which they were randomly assigned to a condition. Their interpupillary distance was then measured. They were given some moments to familiarize themselves with the system, and trials began. After completing the pre-test, calibration, and post-test phases, participants were debriefed. A total of 60 participants took part in this IRB-approved study. Participants were evenly distributed across the experimental design, with 10 participants assigned to each of the 6 conditions. The average age of participants was 27.6 years. 63% of participants were male. All participants had normal or corrected to normal vision. Regarding VR experience, 48 participants reported less than 10 hours of prior VR use, while 12 reported more than 10 hours. Now let's look at results. Participants consistently overestimated dial sizes across conditions. The hierarchical regression model intercept was 82.47 millimeters, even though the average presented dial size was 60 millimeters. This indicates a systematic bias toward larger perceived sizes. Additionally, the strongest predictor of estimated size was the presented dial size itself. This factor significantly predicted the estimated size. As dial size increased, estimates increased even faster, with a slope of about 1.62 millimeters for every millimeter increase in dial size. A significant main effect of perceptual source was observed. Participants in the haptics-only condition showed significantly larger overestimations than those in the vision-only condition. The intercept of the regression model was 82.47 millimeters for the haptics-only condition, while it was 73.27 millimeters for the vision-only condition. This indicates that size estimates were systematically larger when participants relied on touch alone, compared to when they relied on visual information. Calibration produced asymmetric effects across perceptual modalities. In the vision-only condition, estimates increased slightly after calibration. The intercept increased from 68.98 millimeters in the pretest to 70.63 millimeters in the post-test. In contrast, the haptics-only condition showed the opposite trend. The intercept decreased from 80.06 millimeters in the pretest to 77.92 millimeters in the post-test. This suggests that adding visual information during calibration helped improve haptic judgments, while introducing haptic information during calibration sometimes degraded visual judgments. Calibration effects were further moderated by calibration type. In the vision-only condition, both divergent calibration types produced increases in post-test estimates. The convergent condition showed no significant change. In contrast, the haptics-only condition showed decreases in estimates for both divergent calibration types. This indicates improved accuracy after calibration. Again, the convergent condition showed no significant change. These findings suggest that visual information acted as the more reliable perceptual source. Now let's talk about some takeaways. Our results reveal a consistent pattern of size overestimation when participants interacted with tangible dials in near-field virtual reality. This bias was stronger in the haptics-only condition than in the vision-only condition, suggesting that vision provides a more reliable perceptual source for estimating size. Calibration produced asymmetric effects across modalities. When visual information was introduced during calibration, haptic estimates improved. However, when haptic information was introduced into the vision condition, estimates tended to worsen slightly. These asymmetric effects are consistent with information reliability models of sensor integration, suggesting that visual information acted more reliably for size estimation in this task. Taken together, these findings highlight the importance of carefully designing visual haptic calibration procedures when building VR systems that incorporate tangible objects. I take this moment to display and thank all co-authors and collaborators who made this work possible. Thank you for your time.